Let's solve LeetCode 15 3-sum. Given an integer array nums, we want to return all the triplets, that is nums at I, nums at j, nums at k, such that I is not equal to j, I is not equal to k, and j is not equal to k. This is to say that I should not be equal to j, should not be equal to k. And nums at I plus nums at j plus nums at k should be equal to 0. Notice that the solution set must not contain duplicate triplets. Let's take an example. Let's say the nums is -1, 0, 1, 2, -1, -4. The output is this list and this list. Why? That's because if you do -1 plus -1 plus 2, you'll get 0. If you do -1 plus 0 plus 1, you get 0 again. So these are the two triplets that are present, and yeah, that gives us our answer. No duplicate is present here. Notice that the element itself in a solution can be duplicate, but the two elements cannot be directly duplicate, meaning -1, -1, 2 is mentioned over here. It cannot be mentioned again in the list. Okay. And it cannot be mentioned in any form. For example, if you notice, nums at 0 plus nums at 1 plus nums at 2 gives us 0. Nums at 1 plus nums at 2 plus nums at 4 gives us 0. And nums at 0 plus nums at 3 plus nums at 4 gives us 0 as well. So the distinct triplets are -1, 0, 1 and -1, -1, 2. Notice that we have -1, 0, 1 here and 0, 1, -1. Both of them are essentially duplicates of each other. That's why we're not including 3 triplets. We're only including 2 because this and this are duplicate. Even if you don't think it is, you can just think of duplicate as all the elements matching each other. So 0 is present here, 0 is also present here, 1 is present here, 1 is present here, and -1, -1. So they're duplicates of each other, and we don't want to allow duplicates. Okay. Let's take another example. So we have 0, 1, 1. The output is an empty list. Why? That's because if you try to add up something, 0 plus 1 plus 1, you'll get 2. That doesn't make up a triplet, so the only possible triplet does not sum up to 0. Now this gives us valuable insights that can help us optimize our solution, but the thing I'm talking about is that if you want 3 numbers to add up to 0, all the 3 numbers should either be 0 or one of the numbers at least should be negative. Because over here, let's see, we have -1, -1, 2, then we have -1, 0, 1. This is the only way you can have the output coming up to 0. Because think about it, if you have one number which is 4 and then you have 2 or 3, any other positive number will only increase the value. What you need to do is decrease it to get it to 0. So that's what we're talking about here. Now, then we have a third example, which is 0, 0, 0. As I said, if you have 0, 0, 0, that's the only way you can get a triplet where, you don't have a negative number. So this is what we want to solve. I'm just going to copy this entire thing. And I think my computer just froze. Let me just try again. And now let's just copy this thing, paste it in over here, and now let's try to solve it. So the very first solution that would come to your mind is inspired by the 2-sum problem that we've already seen. In there, we used a set, right? And to the set, we added the elements. So we iterated through the entire list, and then we added each of the elements. So -1, okay. And then we checked, hey, is 0 plus -1 equal to 0 or something like that. But even before we begin, hypothesizing what the solution can be, there's one problem. If you use a set, you can't store duplicate elements. And here we do have duplicate elements. There's one -1 here, another -1 over here. And also another problem in sets is that it doesn't maintain an order as such. And we do need an order, correct? Because I is not equal to j, I is not equal to k, and j is not equal to k. So we need to keep track of the indexes to ensure that this set works out, and set doesn't keep track of indexes. Now there are workarounds you can do, but the very first point, that it doesn't allow duplicates, is something that makes us think that yeah, set is probably not a good option. What's another good option then? Well, what if we make use of the problem that is 2sum2, where the input array is sorted. What we did there is first just convert this into a sorted array. So you have -1, -1, 0, 1, 2, and I forgot about -4. So let me just take this thing and just have -4 here. Cool. Now let's see, how can we solve this after we have sorted the entire thing? What I can do is, for every single one item, I can try finding the two pairs that will give us 0. So this way we have 3 elements, right? Because what we want to do is essentially get 3 numbers, x, y, and z, which when added gives us 0. So now first I need to get the 3 numbers, right? And we've seen in previous solutions that like every solution we only had to keep track of 2 numbers. So we know we are very good at keeping track of 2 numbers, which is the left pointer and the right pointer. So what we can do is just hold on to one element. So let's say 4 is kept as a constant, and then we find out the values of left and right, and then find out, what adds up to 0. So let's say we keep 4 as a constant, and then we have a left pointer on -1, right pointer on 2. So we do -4 plus -1 plus negative, and it's not negative actually, plus 2, and we have -3 as the answer. Now is -3 compared with 0? Because 0 is our target value. Now you might notice that this is quite similar to 2sum2, where the input array is sorted, LeetCode 166. And here we're just checking, hey, is -3 greater than or smaller than 0? -3 is smaller than 0. In that case, the left pointer should go over here towards the right, because we want to increase its value. Now we notice another edge case that, hey, I've already checked the value of -1. If I again check the value of -1, that gives us no use. And actually it does a lot more damage than we realize, but we'll talk about it later on. But for now, we can just say that, hey, if we see duplicate elements, we can just skip it. And it's easy to recognize duplicate elements in a list. The reason for that is it's sorted. If it's sorted, that means -1, to the right of -1, there's going to be -1 or something that's bigger than 0. So let's say if this L and L plus 1 are the same, then we're just going to skip it. Okay. So we move to 0. Now we check -4, because remember we have kept this as a constant, correct? So we do -4 plus 0 plus 2. And now we get -2. -2 is still less than 0. So what we do is move our L over here. Cool. We are at 1 now. So we have -4 plus 1 plus 2, which gives us -1, which is still less than 0. And now we finally reach the condition, because R and L are at the same place, and we have kept our condition that, hey, the L should be less than R. So this terminates. But we've still not found our triplets, because in our first iteration, keeping -4 as the constant, we did not get any answers. So now what we're going to do is change our constant. So remember what we have done, just to, put it in straightforward terms, what we did is select one number as constant. So we have one number as constant. Okay. After the one number has been selected as constant, we don't exactly know that the constant value is going to give us the appropriate results or not. It's just hypothesis. So, I'm just assuming at this point. So what I'll do is try to tune the values of L and R, because there's some hope that the constant that I've chosen is correct. So I'll just try and tune the values of L and R according to the 2-pointer technique that we have talked of. If we find anything, good. If we don't find it, what we can do is again go back to the first one and select the second number as K. So now after -4, we'll try -1. Cool. After that, we'll take this -1 as L and this 2 as R, and then we'll again check. Great. So we have -1, -1, 2. That turns out to be 0. So we add it to our final result, that these are the things that we want to store. Now, do we want to store indexes? No, we just want to store the values, and that's good. We can just store the values. Okay. So that saves us one time. Now, let's say we take our L and move forward now, because we found our one solution, but it can be the case that keeping the same constant gives us different outputs as well. So like -1, -1, and 2 was one of the outputs, okay? But there can be the case that -1, some left value and some right value gives us again another 0. For example, let's say we have -4. Sorry, not -4. Let's say we have 4 as the rightmost value and -3 as the leftmost value. This is another of our cases, right, where there's a triplet, because -1 plus -3 plus 4 is equal to 0. So we want to keep going. What we want to do is still keep -1 as a constant and try out other values of L and R to see if we get another answer. Because what we want to do is return all the triplets, not some, all of the triplets. Okay. So let's just copy this again, paste it over here, and as I code it out, I can explain what I'm doing to you. Cool. But I hope you get a brief understanding of what we're trying to do. Selecting a constant and then tuning the values of L and R. If we get a response, store it in our result variable. If we don't get it, try tuning the L and R variables again. If that doesn't work out, then we'll tune the K value, the constant value, to go a further ahead. Okay. Now, I told you that initially the constant value is going to be the very first element. In the second iteration, it's going to be second. In the third, it's going to be third, and so on. So essentially what I'm doing is just a for loop. So what I can do is just check, hey, for I comma num in enumerate, and we'll go over the nums array that's present. In that case, first of all, I'll create a result variable at the top. This is going to be the result variable we return as well. Also, I need to shift to Python 3. Why I didn't shift to Python 3, I don't know. So let me just copy, paste it over here. And now let's go ahead and think of this even further. So once we have the enumerate line with us, what do we want to do? Well, now we have one constant. The num is treated as a constant value for now. I need to figure out the L and the R values, and L is going to be whatever we have at num plus 1, right? I'm not selecting L as this thing only because, well, I don't want two duplicate indexes to be present. For example, the constant value is chosen as -1 here, and then we're choosing the left value also as -1, the same -1. That's not right. We want to set it to something further ahead. And by the way, to set it to something further ahead, we also need to sort the array. And I forgot to do that. So now we have everything sorted. Let me just go back to this one, -1, -1, 0, 1, 2. Again, I forgot to put in -4. So let me just put that in. Cool. So now my constant value, let me just use different colors. So my constant value is over here. Then my leftmost value needs to be assigned to whatever my constant value is plus 1. So I'm going to have, let's say, my L equal to I plus 1. Okay, I indicates the constant numbers index. R is going to be length of nums minus 1 because I always want my R to be pointing towards the end of the array. So let's say this is L and my R is going to be the end of the array. It doesn't depend on this K as of now. After that, what I'm going to do is while left is less than right, we want to keep going. And now I'll just do the same thing I did in this toSum input 2 problem. So what I'll do is compare with the target value, and we are going to first of all do the summation of the triplets. So we have summation equal to num plus the nums at L plus the nums at R. Okay. So what I'm doing is -4 plus -1 plus 2. So I have what? -3. And then we can just check, hey, if summation is less than 0, because 0 is our target value in this case, then we want to do something. If the summation is greater than 0, then we want to do something. Otherwise, summation is equal to 0, and then we want to do something. Now let's figure out what we want to do. If summation is less than 0, that means, we are in this situation where -3 is less than 0. In that case, we want to move the L ahead because I want to increase its value. And to increase the value, I need to move ahead in the sorted array. So what I'll do is L plus equals 1. If summation is greater than 0, I'll just decrease R because I want to decrease the value, right? Because I want to push it further to 0. After that, it is summation equals to 0. That means we have reached a result. So what I'll do is result.append, and to this result, I'm going to append the list. What is the list going to be? Well, let's say it's num, then it's nums at L, and then nums at R. The reason I'm doing this is because num is always going to be less than nums at L is always going to be less than nums at R. The reason for that is I is always going to be less than L, which is always going to be less than R. That's because of the restrictions we've put in. Because L is always less than R, that's the restriction we've put. And I is always going to be less than L because L is always I plus 1 or further ahead. Cool. So that is our result, but that, just solves our problem for the best case scenarios. And unfortunately, most cases are not best case scenarios. So what are we missing here? What we are missing is this line. Notice that the solution set must not contain duplicate triplets. In this scenario, duplicate triplets can exist. How? Well, let's go over it. Now we already have gone through this, so we know -4 has no solution. So let's just take everything one step further. So I don't think I'm able to capture this properly, but let's say we are somewhere over here. Okay. R is the only thing that remains constant, but K and L move further. Now what we have is -1, -1, and 2. That's cool. But now let's say we have in our result, and let me just copy -1, -1, 2. Cool. Now what we do is move L ahead. Okay, because we have found a solution. So what we say is that, hey, if I found my solution, I'll just move L plus equals 1. And that's something we have not done here. And this brings us to an infinite loop because as soon as we find a solution, we just append to result, and then we go in this loop again where L and R none of them has changed. So again, we go through the same condition, the L is the same, R is the same, so we get the same summation, which is 0, and then we again execute this case, leading to an infinite loop. So in this case, we either need to do L plus equals 1, or you can do R minus equals 1. Either one of them will work, but I just prefer to do L plus equals 1 so that, I move forward ahead. That's more intuitive than just moving behind. So like just R moving behind is less intuitive, but it's your choice. Doing R minus equals 1 also works. Cool. So now let's take another situation. So we have -1, 0, and 2. So in this case, we have 1 is less than 0. That's not true. 1 is greater than 0. So that would mean that R needs to get up and move ahead. Cool. And now we get the answer of -1, 0, and 1. So we'll store that in our array. Cool. So we have two answers. That's great. And also we have exhausted all of our tries here because, well, if we move this L to 1, we're not really going to get answers anymore. We know that already. So I'm not going to waste much more time on this and just move K ahead. So now what I'm going to do is shift our K to another -1, and that's where the real problem is going to exist. I hope you can already see the error, but what I'm talking about is this. Let me just remove this, nothing extra. So the error I'm talking about is in this case, K plus L plus R. What is it going to give us now? It's going to give us 1. 1 is greater than 0. So that would mean R again shifts, and this is R now. It's not this anymore. So now we do -1 plus 0 plus 1, and that gives us, and that appends to the result. So we have -1, 0, 1 in the result, and there are 2 duplicate elements. That's not allowed. It shouldn't be allowed. And the core reason for it is what? It's because we're using -1 over here. We're also using -1 over here. If you continuously use -1 and rest of the elements are going to remain the same, we will get the same results. So whatever results you got for this -1 will be the results for this -1. And we can't take that risk. So what we need to do is remove the duplicated elements. So we want to put a check that, hey, if the previous element was the same element as this one, so that means this -1 is equal to this -1. In this case, what we are going to do is just skip this particular element because we've already seen the possible combinations that will give us a triplet. So to solve this, what we're going to do is at the very top, before we initialize L and R, we will just check, hey, if the nums at I is equal to the nums at I minus 1. In that case, I will ignore. And even doing this is bug prone because think about it. If your I is 0, then you're doing nums at 0 minus 1, which takes element from the last. And we don't want to allow that. So what we want to do instead is this. If I is greater than 0 and nums at I is equal to nums at I minus 1, then we want to continue. We'll just skip if the elements are the same. And we can do the same check over here as well after the else case. So after the else case, we have done L plus equals 1. And that moves our element to the forward case. So let's say -1, 0, 1 was the solution we got. So we moved L forward, right? Or actually, to explain this better, I'll just clean stuff up. So let's remove this out. Cool. So let's say our solution was this. This was K, this was L, and this was the R. That gives us a solution because all three added up is 0. Now, let's say we did L plus equals 1, and actually this problem wouldn't give this issue, but let's say we had more negative ones in place. In that case, it would really give us a problem, because let's say we had an error, or we had an array like this: -4, -1, -1, -1, -1, 0, 1, 2, 2. This is quite possible, right? So in this case, we found out -1, and this was L, and this was our R. Okay, so that gives us 0, and then we say L plus equals 1. So yeah, this is L, and we essentially land onto the same problem. We don't want to land onto the same problem, right? Because we want to skip all of these duplicated elements. So what we are going to do is, after we move ahead one place, we'll just check, hey, while the number that you have, which is nums at L, is equal to the nums at L minus 1, then what I want to do is L plus equals 1. So I'll just keep moving ahead so that I don't face any duplicate values. Okay. And also I'll just put another check here, which is and L is less than R, because I don't want L to exceed R while, we are doing plus equals 1 again and again. So this is something that I'll do. Now let's try running it, and hopefully it works. Actually, it won't work out because I forgot to return result. So let's return result from here, and let's try it now. And the answer does fail. Let's understand why. And I just realized what the issue over here is. And the issue is that I've returned result within the indentation of this for loop. Actually, I should be returning it outside of the for loop. Now, if I run it, it should work out. Yep, it does. I'll click on submit. And that works out as well. And if you see, the runtime and the memory are pretty good. Now, what's the runtime over here? The runtime is not O of n. It's not O of n log n, because we have sorted it over here, right? No, in the worst case scenario, it is O of n square, because for each number, you're keeping one as a constant and trying to find the next number, or next two numbers actually. So you just keep doing that. So for each n, you're trying to find two numbers which will take another O of n time. Okay. And what is the space complexity of this? The space complexity, as you can realize, it's O of 1. Now, just to prove it to you that just changing R would also work, I'm just going to do R minus equals 1. So when the cases match, we just do R minus equals 1, and then we do while nums at L is equal to nums at, well, we'll not do L, we'll do nums at R is equal to nums at R plus 1. Because whenever we find an element, what we are doing is, instead of doing L plus 1, so if L was here, L would move over here. That's not what we're doing. We're doing R was here, R will move one step behind. So it will move towards the beginning of the array. And then we want to compare that, hey, if this number was already taken care of, I will ignore it. So if nums at R is already taken care of, nums at R plus 1 should not be taken care of. Or actually, if nums at R plus 1 was taken care of, nums at R shouldn't be taken care of. So I'll just do R minus equals 1 here. And then we can just run this, and yeah, it will work out. So yeah, that is the solution. Again, the time complexity here is O of n square plus n log n because we are also sorting it. But yeah, the bigger thing is O of n square, and the memory complexity is O of 1.